Hello everyone, welcome to new class. Today's class is types of DC generators. So in the previous class we have discussed about the EMF equation of generator. So if you didn't watch it, please go through it. So let us go through the class. The generators are usually classified according to the way in which their fields are excited. So on this basis, the DC generators are divided into two, that is separately excited DC generator and self-excited DC generator. Separately excited generators. The separately excited generators are those whose field magnet winding is supplied from an independent external DC source. So this is the connections of a separately excited DC generator. The greater the speed and the field current, greater is the generated EMF. So here IA is the armature current and that is equal to load current IL. So armature current IA is equal to IL and terminal voltage. So this is terminal voltage, that is the voltage across the load. So terminal voltage V is equal to, here EG is the generated EMF and RA is the armature resistance. So the terminal voltage V will be equal to EG minus IARA, because there will be a drop in the armature resistance. So we have to subtract that drop to get the terminal voltage V. And electrical power developed is equal to EG into IA, that is the power developed is EG into IA. Then the power delivered to the load is equal to V into IL, that is voltage into current V into IL, but IL is equal to IA, and also we can write this V into IL is EG minus IARA. So we can write EG minus IARA into IL, but IL is equal to IA. So we can write EG into IA minus IA square into RA. So this is the power delivered to the load V into IL. IL is equal to IA. Next is self-excited generators. A DC generator whose field magnet winding is supplied from the output of the generator itself is called a self-excited generator. And there are three types of self-excited generator: series generator, shunt generator and compound generator. So first one is series generator. In DC series generator, the field winding is connected in series with the armature winding. So let us draw the armature. Here the field winding. So this is the field winding and the field winding is connected in series with the armature winding, and this is the load. So here the whole armature current flows through the field winding. So here the whole armature current flows through the field winding, and this is the terminal voltage. So this is R series. Then Eg is the developed or generated EMF. Then Ra is the armature current. Ra is the armature resistance. Ia is the armature current. Then here we can write this armature current Ia. Ia is equal to the current flowing through the series winding, that is ISE, and which is equal to IL, that is the load current, and we can represent it with the capital letter I. So armature current Ia is same as the load current. Then the terminal voltage V is equal to Eg minus the drop in the armature resistance and the drop in the series resistance we have to consider. So here it is I into Ra plus Rse, or we can represent this I with Ia or IL. So let us write with Ia, and that is equal to and the power developed in armature is equal to Eg into Ia. Then the power delivered to load. So power delivered to load will be V into IL, and V is Eg minus Ia into Ra plus Rc. So we can write Eg minus Ia into Ra plus Rse into IL, or IL is equal to Ia. So we can write Eg into Ia minus Ia square into Ra plus Rse. So this is the power delivered to the load in the case of series generator. Next is shunt generator. In DC shunt generator, the field winding is connected in parallel with the armature winding. That is, this is the armature winding. Then the field winding is connected in parallel with the, this is field winding. Let it be, the resistance be RSHS. So here the field winding is connected in parallel with the armature winding, so that the terminal voltage of the generator is applied across it. So here the terminal voltage will be same as the voltage across the field winding. And the shunt field winding has many turns of fine wire having high resistance, and only a part of the armature current flows through the shunt field winding. And let ISH be the current through the shunt field resistance. Then IL is the load current. So this is the load. Then EG is the developed or generated EMF. Then IA is the armature current, RA is the armature resistance. Then we can write ISH. So here the shunt field current ISH is equal to V divided by RSH, because the terminal voltage is applied across the field winding. So ISH will be equal to V divided by RSH, and armature current IA is equal to the sum of these two currents, that is ISH plus IL. Then the terminal voltage V is equal to, it is EG minus the drop in the armature, that is IA into RA, and power developed in armature is equal to EG into IA, and power delivered to load is equal to V into IL, where V is equal to EG minus IA into RA. EG minus IA into RA into IL. So here IL is IA minus ISH. Next is compound generator. In compound generator, there are two sets of field windings on each pole. One is series and other is parallel with the armature. So there are two types of compound generator. One is short shunt and next is long shunt. So in short shunt compound generator, the shunt field winding is parallel with the armature winding. So this is short shunt compound generator. So here the shunt field winding is parallel with the armature winding. Whereas in long shunt generator, the shunt field winding is parallel with both series field and armature winding. So this is the long shunt compound generator. Here the shunt field winding is parallel with the series field and armature winding. So in the case of short shunt compound generator, EG is the generated EMF, RA. So this is RA. RA is the armature resistance, IA is the armature current. Then RSC is the series field winding, RSH is the parallel or shunt field winding. Then let IL be the load current and this is the ISH. So here ISC is equal to IL. ISC is equal to IL, and here we can write IA is equal to ISH plus IL, and ISH, we can write ISH as the shunt field current ISH equal to this voltage, and that is equal to terminal voltage V plus the voltage drop in the series field. So V plus, either you can write ISC RSC or IL RSC. So ISC into RSE divided by RSH is the shunt field current. Then the terminal voltage V is equal to EG minus the drop in the armature resistance plus the drop in the series field. So we can write ISC RSC minus IA RA. And power developed in armature is equal to Eg into Ia, and power delivered to load is equal to V into IL. So this is the case of short shunt compound generator, and in the case of long shunt, this is Eg, the generated EMF, Ra is the armature resistance, Ia is the armature current, and which is equal to the series field current ISC. Then this is the load current IL, and this is the shunt field current ISH. So here IA is equal to ISH plus IL. ISH plus IL. Then we can write the shunt field current ISH. ISH is equal to this terminal voltage V divided by RSH, because here this terminal voltage drop is equal to the voltage drop in the shunt field. Then V, the terminal voltage V, we can write Eg minus the voltage drop in the armature resistance and voltage drop in the series field. So we can write Ia into Ra plus RSE, and power developed in armature is equal to Eg into Ia, and power delivered to the load is equal to V into IL. So this is the case of long shunt compound generator. And in compound generator, the shunt field is stronger than the series field, and when the series field aids the shunt field, the generator is said to be cumulatively compounded. So when the series field aids the shunt field, the generator is said to be cumulatively compounded, and if the series field opposes the shunt field, the generator is said to be differentially compounded. Next is conditions for build-up voltage in a shunt generator. The conditions are: there must be some residual magnetism in the poles. Then second one, flux produced by the shunt field winding should aid the residual flux. Then third one, the resistance of the shunt field winding should be less than a particular value, and this value of resistance is called field critical resistance. So this is about the types of DC generators. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.